Hi, my name is Raj Chakrabarty, and I'm a senior at Upper St. Clair High School. Today, I will be talking to you about the elimination of static in plexiglass. You've all seen plexiglass, the transparent, tough, non-brittle plastic which finds many applications in which its toughness often makes it preferred over glass. There is, however, one major problem with plexiglass, and this is that it is relatively soft and scratches easily. It is also very prone to static development. If you rub plexiglass against another object, it develops static, and this static attracts dust. The dust attraction is a nuisance, but more than that, when you try to clean it off by buffing, it acts like an abrasive and scratches the surface. Thus, you may start off with a super transparent surface like this, but end up, after buffing, with a more hazy surface like this. The purpose of my study was to find a way to modify the surface of plexiglass so that it does not develop static. If this can be done, the utility of plexiglass will be significantly enhanced. But before I discuss the technical approaches that I utilized or investigated, please allow me to first review what causes static. Static is caused by the flow of electrons from one kind of a material to another when they are rubbed against each other. Thus, when you rub plexiglass against, say, silk, electrons flow from the plexiglass to the silk, causing both materials to become electrically charged. If the surface of either material is a non-conductor of electricity, as is the case with plexiglass, this charge cannot be dissipated and manifests itself as static electricity, scientifically known as triboelectricity. This slide shows several materials arranged in a triboelectric series. When two materials in this series are rubbed against each other, the one which is higher in the chart becomes positively charged, and the lower one becomes negatively charged. The chemical name for plexiglass is polymethyl methacrylate. As you can see, it lies in the upper segment of the chart. I took two approaches to eliminate static from plexiglass. The first was to treat it topically with surface-active chemicals, called surfactants in short, and to see if they could provide surface conductivity. My second approach was to chemically modify the surface of plexiglass and to see if it could dissipate the charge. But first, a few words about surfactants. This slide shows a graphical representation of a surfactant molecule. These are molecules which have a long hydrophobic or water-hating segment which contain the elements carbon and hydrogen, and a hydrophilic or water-loving segment which contains such elements as nitrogen, oxygen, sulfur, or combinations of these three elements. Depending on the ionic character of these hydrophilic groups on the surfactant molecules, a surfactant can be classified as an anionic, a non-ionic, or a cationic surfactant. This slide shows examples of each of these three types of surfactants. The use of surfactants as topical antistats is not new. Polyethylene films, for example, used for treating electronic materials or packaging the electronic materials, are treated with non-ionic surfactants to eliminate the static charge. Why surfactants act as antistats is not quite clear. In the case of polyethylene, the antistatic effect of lauryl diethanolamide has been explained as follows. Surfactant molecules are believed to absorb themselves onto the polyethylene film shown here, with their hydrophobic ends facing toward the film and their hydrophilic groups facing away from the film. These hydrophilic groups then bond or absorb a thin layer of water through hydrogen bonding, and this layer of water dissipates the static electricity. This is the case with polyethylene. In the case of plexiglass, however, known record is available in the literature on the effectiveness of surfactants as topical antistats. One more thing about the surfactants, and this is that the treatments that the surfactants bring about are fugitive and can be readily washed away with water. The antistatic effect on the substrate is thus lost with time. My first objective was to screen a wide variety of surfactants on plexiglass and to determine which, if any, works best. Before I describe my experiments, allow me please to first emphasize the importance of humidity control on static measurements. The degree of static developed by a surface depends to a great extent on humidity conditions. Thus, in the winter, when humidity is low, static is most prominent. Because of this dependence of static on humidity, I conducted all static measurements under rigorous humidity control conditions. I designed a special humidity control chamber using a glass aquarium and a plexiglass cover. The humidity inside this chamber was controlled by placing 150 grams of anhydrous calcium chloride inside an open wide-mouth bottle and placing this bottle within the aquarium. All test samples were conditioned inside this chamber before static measurement. The room in which the experiments were carried out was also maintained under rigorous humidity control conditions, namely 65% relative humidity and 75 degrees Fahrenheit. This was achieved by using a dehumidifier and an air conditioner. The plexiglass test samples that I used for most of the experiments were 4-inch by 4-inch squares like this. To store them, I designed a special oak storage rack with appropriate grooves. This rack was designed in such a way that it could comfortably fit within the humidity control chamber. Now for the measurement of static. Because no standard procedure was available for quickly measuring static on the plexiglass plates, I devised two tests, one for measuring the propensity for static buildup and the other for the rate of static decay. The first test used for measuring the propensity for static accumulation was a modification of the popular cigarette ash test, which consists of rubbing the plastic against another surface to generate a charge and then holding the plastic immediately over a shallow dish containing cigarette ash. The presence of static charge manifests itself through vigorous jumping of the ash onto the charged surface. My modification consisted of replacing the cigarette ash with fireplace ash. For this test, I used the 4-inch by 4-inch plates I showed you before. I generated static by rubbing the plates against daily newspapers that had been conditioned at 65% relative humidity inside the humidity-controlled room for 48 hours. As shown here, I used 15 medium-pressure, 12-inch strokes for each sample. The samples were immediately held over a shallow dish containing cigarette ash, and the extent of ash pickup was noted. The samples were rated on a scale of 0 to 4, with 0 being no static buildup or no ash pickup consequently, and 4 being the heavy static buildup characteristic of untreated plexiglass. A similar test was conducted using house dust collected from a home vacuum cleaner in place of the fireplace ash to represent real-life dust conditions. For the samples that showed the best performance in the ash dust test, a second test was used to measure the rate of electrostatic decay. This was a modification of the popular American Association of Textile Chemists and Colorists test, called in short the AATCC test number 115-1986, a test which was originally designed to test or measure the electrostatic clinging of fabrics to metal. In the AATCC test shown here, a test fabric, which is usually rayon, is allowed to cling to a grounded metal plate inclined at an angle of 70 degrees to its base, and the time for declinging of the rayon fabric is measured. My modification consisted of 1, replacing the inclined metal plate with a similarly inclined plexiglass plate, which was made by heat bending a plexiglass strip. I also substituted for the taffeta rayon fabric a piece of grounded aluminum foil which had a weight attached to the lower end. Static was generated using a piece of white pine, a white pine block, which was wrapped in taffeta rayon fabric. To generate the static, I rubbed the long arm of the inclined plexiglass plate with the taffeta rubbing block 15 times. The plate was then turned upright, and the aluminum foil was allowed to cling to the surface of the plexiglass. The time between this point and this point, where the aluminum foil is hanging freely, was measured and recorded. The test procedure for evaluating surfactants consisted of rinsing plexiglass plates with 1% solutions of surfactants in 91% isopropanol. The samples were immediately blot dried by pressing them between Kleenex tissues. They were then conditioned under 15% relative humidity at 75 degrees Fahrenheit before measuring their static behavior. After static was measured on the 4-inch by 4-inch samples, they were rinsed with distilled water, dried, conditioned, and tested again for static behavior to see if the treatments were fugitive or not. A duplicate set was heat treated at 100 degrees Celsius for 10 hours, or for 2 hours, excuse me. These samples were also tested for static before and after washing to determine the effect of heat treatment on static. This slide shows the different surfactants that were tested along with their chemical structures in this column. This slide shows their performance as static control agents on plexiglass. The first set of numbers in each of these columns represents the data collected from the ash test, and the second set of numbers, the data collected from the dust test. As you can see, there was not much difference between the data collected from these two samples. The first two columns in this chart shows the data that was collected before the samples were washed. Once again, the samples were divided into two sets, one set which was heat treated and the other which was not heat treated. The second two columns represented data that was collected after washing. Once again, the same two sets were tested and the results were recorded. As can be seen, the cationic surfactants as a group, represented by samples number 15 and 16, showed excellent static elimination. A select group of non-ionic surfactants, samples number 13 and 14, also showed excellent static elimination. Only one anionic surfactant, sample number 4, showed decent static elimination. It may also be noted that heat treatment did not alter performance. It may further be noted that after the samples were washed, regardless of whether they were heat treated or not, all samples lost static protection. The surfactant samples that performed well, namely samples number 13, 14, 15, and 16, were also tested by the rate of static decay test. For this test, the inclined plexiglass pieces that I described before were treated with the surfactants in essentially the same way that the 4" by 4" samples were. The results of the static decay tests are shown in this slide. As you can see, the control samples showed over 300 seconds or over 5-minute decay times. Those samples that showed excellent static elimination or total static elimination in the ash and dust test, samples number 13, 14, 15, and 16, likewise showed instantaneous static decay times. Since static control by surfactant treatment could at best be fugitive, I next tried to chemically modify the surface of the plexiglass so that it could become permanently anti-static. To understand the reaction that I investigated, let's first look at the molecular structure of plexiglass, which is made by polymerizing methyl methacrylate into polymethyl methacrylate, or plexiglass. The reaction that I concentrated upon consisted of reacting some of the methyl ester groups shown here on the plexiglass with diethanolamine. Once again, as I just said, this methyl ester groups on the plexiglass surface are reacting with diethanolamine, resulting in a surface-modified plexiglass with the hydrophilic groups permanently bonded to the surface. You may notice that these hydrophilic groups resemble those that I showed you on the surface of the polyethylene film earlier. The chemical reactions on the plexiglass surface were carried out as follows. First of all, the plexiglass pieces were dipped inside diethanolamine containing a trace amount of sodium methoxide catalyst. And this mixture was placed inside a 6-inch diameter Petri dish. The Petri dish, in turn, was placed onto a 12-inch by 12-inch glass plate. Then another larger Petri dish was placed on top of the entire assembly I just showed you, and the edge of this assembly was sealed with the silicone caulking shown here. This entire assembly was then placed inside an oven to be heated at a desired temperature. After the desired reaction time, the samples were removed. First, to be washed, as shown here, with cold running tap water and then with distilled water. They were then wiped dry with Kleenex tissues and conditioned for 24 hours in the 15% relative humidity chamber before measurement of static. The results of these tests are shown in this slide. As you can see, those samples that were reacted at room temperature for 48 hours showed no elimination of static, thus showing that no reaction took place. Those samples that were reacted at 80 degrees Celsius for 6 hours showed decent static elimination, and those that were reacted at 100 degrees Celsius for 10 hours showed total elimination of static. This slide shows a direct comparison. The sample on your right is one that was treated at 100 degrees Celsius for 10 hours. The one on your left is a control sample. The slight haziness you might notice on the sample on your right is only due to the flash on the camera. Remember that these samples were thoroughly washed before conditioning in the humidity control chamber, and testing for static, of course. The results I saw were thus permanent. In conclusion, I'm happy to say that I've been able to achieve both the objectives that I set out to fulfill. One, I've identified the best surfactants for elimination of static on plexiglass by topical treatment. I found, as expected, that surfactant treatment, even by the best surfactants, is fugitive. I've also shown that permanent static elimination can be achieved by appropriate chemical modification of the surface of plexiglass. This second observation, I believe, is novel, and I plan to file a US patent application on this invention. My thanks are due to Mr. Edward Callahan, my science teacher, for his encouragement, to Mr. William Williams of PPG Industries for kindly lending me the AATCC metal test plate, and to the companies listed here for kindly lending me with the surfactant samples that I needed. And I thank my parents for building me this laboratory since I was 10 years old. Thank you for giving me the opportunity to present this paper.